All right, today we are diving headfirst into a topic that sounds like it's been pulled straight from a sci-fi novel. But believe it or not, this is happening in real labs right now. We're talking about something called Polaritonic quantum matter, a field where scientists are literally engineering new forms of reality by fusing light and matter together.
So just think about that for a second. What if that fundamental line we all learn about between light and matter could just be blurred? What if you could actually merge them, creating a brand new hybrid particle that's part light and part matter? It sounds totally impossible, right? But this strange new reality is being built as we speak. So how do we even begin to wrap our heads around this?
Well, to understand this new reality, you have to meet the star of the show, the polariton. It's this very special particle, or to be more precise, a quasi-particle, that's at the heart of this whole thing. It is a true hybrid, born from two completely different worlds.
And this isn't some brand new out-of-the-blue idea. This actually goes all the way back to 1958. A physicist named John Hopfield first came up with this radical concept of a strange, dual-natured particle. He basically laid all the theoretical groundwork for the incredible things we're seeing today.
So what is a polariton, really? Well, it's what's known as a quasi-particle. Now that sounds a little intimidating, but it just means it isn't a fundamental particle like an electron. Instead, it's a kind of emergent phenomenon that pops into existence when other things interact in a very specific way. In this case, it's born when a photon, a particle of light, gets deeply entangled or strongly coupled with some kind of excitation inside of material. I love the analogy of light getting dressed in the properties of matter. It borrows some of matter's traits, and in return, the matter gets to act a little bit more like light. You really do get the best of both worlds.
Okay, I know this diagram looks a little complicated, but what you're seeing is the magical moment a polariton is actually born. So imagine you have two lines. One is the energy of the light, the other is the energy of the matter. Now normally, those lines would just cross over each other, but not here. When they get close, they actually repel each other. They push each other apart. This creates a gap, which has the cool name Rabi splitting, and two brand new energy paths are formed. And those are our new hybrid states, the upper polariton, or UP, and the lower polariton, LP. This avoided crossing is the smoking gun. It's the definitive proof that you've done it. You've made a polariton.
And here's where it gets even more interesting. It turns out the polariton isn't just one type of particle. It's an entire family, a whole diverse group of them, and it all depends on what kind of matter you decide to pair the light with.
This slide just illustrates that versatility perfectly. I mean, look at this. On the left, you've got a very natural system, a single atom playing the role of matter. But then, on the right, you've got a completely man-made artificial atom, a really complex superconducting circuit. The takeaway here is incredible. The matter half of this recipe can be almost anything, from the most fundamental building blocks of nature to super sophisticated pieces of technology we build ourselves. This flexibility is really what makes the whole field so incredibly powerful.
So let's quickly meet the family, shall we? Depending on what you mix your light with, you get a totally different flavor of polariton. Mix it with semiconductors, you get exciton polaritons. Mix it with the vibrations in a crystal, which are basically like sound waves, you get phonon polaritons. You can even use the electrons in metals, the spin waves in magnets, or even the qubits from a quantum computer. Each member of this family has its own unique personality, and each one unlocks a whole different set of possibilities.
Okay, so now we know what they are. But the real question is, what can they do? This is where it gets really, really exciting. Because by mixing light and matter, polaritons get these incredible superpowers that allow them to literally rewrite some of the fundamental rules of physics.
Superpower number one, the ability to create what scientists are calling topological highways for light. This is basically a way to guide energy and information with almost perfect efficiency, which is something that's incredibly difficult, if not impossible, to do with just light on its own.
And this image shows a fantastic example. What scientists did here was create a material that looks like a honeycomb. They call it Polaritonic graphene. Now here's the superpower. In this special structure, polaritons can only travel along the edges and only in one direction. Because this flow is topologically projected, which is just a fancy way of saying it's incredibly robust, it doesn't care about any bumps or defects in the material. The energy just keeps on going. It's a perfect one-way street. I mean, imagine data flowing through a circuit without any loss or interference. That's the kind of power we're talking about here.
The second superpower is, well, it's even more profound. It's making light particles, photons, actually interact with each other.
You see, normally, photons just pass right through one another without a second thought. They are famously antisocial particles. But polaritons? They change all of that.
The secret to making these antisocial photons finally interact is something called the blockade effect. See, because polaritons are part matter, they inherit some of matter's social rules. And the big rule for matter is two things can't be in the same place at the same time. The same thing applies to polaritons. Once one polariton occupies a certain energy state, it blocks any others from joining it. It's this really simple rule that, for the first time, gives us a way to make particles of light actually talk to each other.
And here's how scientists are cranking that interaction up to 11. They use something called a Rydberg atom. So think of a normal atom as a tiny solar system. Well, a Rydberg atom is one where the outermost electron has been kicked into a gigantic orbit, making the whole atom puff up to an enormous size. So when you make a polariton with one of these puffed up atoms, it inherits that huge size. This creates a massive personal space bubble around it, a huge blockade. And this means one polariton can influence another one from very, very far away, which is the absolute key to building things like the logic gates you'd need for a quantum computer that runs entirely on light.
And if that wasn't enough, here is a truly wild idea for you. Some physicists think that certain types of polaritons might be sensitive enough to actually detect axions, a hypothetical particle that's one of the leading candidates for dark matter. Now, it's a long shot, for sure, but just imagine, these tiny engineered hybrids of light and matter could be our key to finally cracking one of the biggest mysteries in the entire universe. So, where's all this heading? Well, we're really moving beyond just discovering these particles. We're now actively using them to engineer entirely new materials and, in a very real sense, engineer new realities.
And the big idea driving this future is called cavity materials engineering. It's a simple concept, but it's incredibly profound. The idea is that just by putting a material between two mirrors inside a cavity, you can force it to interact with the light trapped inside and form polaritons. And that process, all by itself, can fundamentally change the material's most basic properties. The crazy part is, you don't even need to shine a laser on it. The material itself gets re-engineered from the ground up just by being in the right environment.
And the possibilities here, they're truly staggering. Imagine being able to steer a chemical reaction to get the exact molecule you want, or taking a totally normal material and giving it the property of superconductivity, just by sticking it in a cavity. This is the path we're on, towards revolutionary quantum computers, and maybe, just maybe, finally understanding the deepest rules of how light and matter dance together.
By creating these strange, powerful light-matter hybrids, we've unlocked a completely new toolkit for controlling the world around us. We're no longer just observers of reality, we're actually becoming its architects. And that really leaves us with one final tantalizing question. Now that we know we can do this, what other fundamental rules of the universe are just waiting for us to rewrite them?